Hi there, from all of us here at CalNext Solutions, and welcome to an overview of ORAN synchronization testing requirements and solutions. First off, let's very quickly take a look at an overview of the synchronization architectures for the defined lower layer splits. So for a C1 configuration, we've got the ODU and the ORU directly connected. Synchronization is going to flow from the DU to the RU, a Ethernet link carrying PTP or SYN key. Configuration C2, and this is one which I think is going to be pretty common in deployment. We have a front haul network in between the devices, so the sync flow is still in the same direction. Intermediate devices participating or having an effect, certainly, on the synchronization performance. C3, here the front haul network is an intermediary, delivering synchronization outwards to both the DU and the RU. And for configuration C4, independent synchronization flows sources to DU and independently there, the RU. So I'd like to take a deeper look at that C2 configuration. It's going to give us a good example where we can look at the time and frequency budgets for the equipment, for network performance, how these all fit together, and what that means for testing a device. So ultimately, on the air interface, a relative time error requirement between these 2 points, all the way back into the network for the C2 configuration. Remember, there's synchronization delivered into the ODU. In practice, this is likely to be mobile backhaul network. Therefore, there are well-defined requirements here for synchronization in ITU-T. 8271.1.c, that's going to be the input to the ODU. And there you've got a maximum time error filtered metric and a limit of 1.1 microseconds. Then if we take a look at table 9.3, from the ORAN specifications here for synchronization, we can see the relative time error performance which is needed on the output from the front haul network and the input to the ORU, and also there for the performance that's required for that front haul network segment itself. Let's remember also there is a frequency requirement on the transmission here on the air interface, and that's going to work its way all the way back through the network. So for the ODU itself, that output is going to have a specification for the frequency error that it can contribute. So in terms of timing performance, one of the key things that this ODU is going to need to do is to apply correctly a sub-millihertz low-pass filter. That input network, that input timing performance meeting that ITU-T requirement, it's actually going to be a noise pattern there, so that ODU is going to be able to tolerate that. And then on that output, again, we've got that requirement. So an example being the 5 part per billion frequency error requirement. If you want to go further, there's also specifications in ITU-T for the performance of that kind of equipment. And you can see here that in the longer duration of testing, we've outlined the lower limits there. So there's kind of a combined performance that you may want to reach to deliver this overall network performance. Breaking that down a little further, looking specifically at the timing capabilities of the ODU itself, you can see here, simplifying the system, somewhere upstream, there's going to be a PTP master device, a subordinate clock function within the ODU, and the equivalent on the downstream interfaces. So again, the input's got to be able to tolerate time error as defined in the ITU-T standard 8271.1. It's going to be a particular time error pattern. And under those conditions, the PTP output should meet this 5 part per billion limit, ideally also those ITU-T performance limits indicated by the lower part of these combined masks here. So note that the level of accuracy here for making this measurement is down to a nanosecond to be able to make sure you can accurately see the performance of the device, a key point there. So testing that timing performance with an ODU. Paragon Neo here, emulating sub-nanosecond accuracy, the PTP master, making a timing measurement on the subordinate side, again to sub-nanosecond accuracy, producing the required metrics, measurements, testing to limits, all of this while applying that defined time error noise pattern on the input to the ODU which is being tested. So let's take a look at that now. Here you can see selecting the desired interfaces to be tested, mixed rates being a clear requirement for an ODU and its position in the network. Here you take control of the PTP clock emulation function, set up an ITU-T compliant profile. Here selecting that specific noise pattern, starting the measurements, taking a look at those real-time metrics, and ultimately getting the pass result, hopefully, from the ODU under test. So here we can select the relevant metrics that we want, get deeper analysis, look for that mask that we want to confirm a pass to, and zoom in to see clearly that it's a pass. In summary here, we have a complete PTP and Sync test solution, a range of functions available for testing, for example, ODUs, ORUs to ORAN requirements, also ITUT-defined telecoms boundary clocks, Class C and Class D level performance, continuously developing test case-driven workflows for ORAN, ITUT, and other synchronization standards, and other features and benefits like test report generation, capabilities for developing network technologies such as network slicing with FlexE and the synchronization requirements of those, and an interoperability with the wider Calnix portfolio, offering options for real-world time error capture and replay. For more information, please feel free to contact us or visit our website. Thanks very much for your time. Goodbye.